Hello everybody, I am S.K. Tiwari, Adjunct Faculty, Department of Geology, Banaras Hind University, Varanasi. So, I welcome you all in this session which is on precipitation to groundwater. We all know that water is one of the commonest, but it is one of the most complex substances which is present on the Earth's surface. This water is present in all the three phases, that is, water is present in liquid form, it is present in solid form in the form of ice, in gaseous form in the form of water vapor or moisture. The chemical structure or formula is H2O, D2O or T2O as shown in the diagram. So if we look at the position of the phase diagram of water, it very clearly appears that on the high pressure zone of the triple point we get water vapor in the form of solid ice. Above the triple point, it is present in the liquid form which is known as water. Right hand side of the triple point, that is towards the higher range of temperature, we get the H2O in the form of water vapor. So it very clearly appears that they are present in all the three phases, that is liquid, solid and vapor on the Earth's surface. So now if you look at the hydrologic cycle, which is nothing but endless circulation of water, because of this hydrologic cycle, we get purified water through the process of purification through air, evaporation and rain. This is nothing but continuous movement of water above, on and below the Earth's surface. If we look at the water availability and its distribution, it appears that this water is present at two places, one on the surface of water in the form of fresh or saline water, as well as it is also present below the surface of the earth in the form of subsurface, which is also known as groundwater. Now just to remind you about the hydrologic cycle, we all are aware that from the heat which is received from the sun in the form of solar radiation, the water which is present above on the surface of the earth in the form of different water bodies in the lakes, in the rivers or in the oceans gets heated and they are evaporated, which ultimately forms cloud after the condensation of the water vapor. This cloud, when precipitates above on the surface of the earth, they flow in the form of surface runoff, as well as some part of it percolates downwards and goes subsurface. So these are some diagrams or schematic representation of the hydrologic cycle. Now, if you look at the distribution of rainfall in India season-wise, it very clearly appears that a majority of the rainfall, that is about 73.7% of the rainfall, is because of the southwest monsoon during the period of June to September. About 13.3% of water is received by the post-monsoon, which is in the time duration of October to December. About 2.6% of the rainfall is because of northeast monsoon during January to February, while about 10% of the rainfall we get by the pre-monsoon rains during the period March to May. Now, it is very important if we are going to talk about the hydrological studies. We have to generate the data related to rainfall, as well as we have to analyze the generated data. For this, we need data collection centers in the form of rain gauges. These rain gauges have been established by a number of agencies. For example, we have established rain gauges by Indian Meteorological Department, by Public Works Department, also by Irrigation Department or Agricultural Department, Forest Department. Even at the administrative level, the Additional District Magistrate Office collects the data related to rainfall. Not only this, also one of the very important magazines, Sankheki Patrika, is also published by the Government of India, which contains rainfall data. Now, if we look at the length of record or the number of years which is needed to obtain a stable frequency distribution of rainfall, depends upon the type of catchment area or the catchment layout. If the catchment area is islands, we need the data of at least past 30 years. If the catchment area is along shore, we need the data of at least 40 years. If the catchment area is planar in nature, we need the data of at least 40 years. Similarly, if the terrain is mountainous in nature, we need the data of last 50 years. Now, we'll talk about the density of the rain gauge. The density of rain gauge depends upon the catchment area. That is, the catchment area per gauge should be small. For this, there are a number of recommendations. For example, we have recommendations, international recommendations like 4987, which was adopted in 1968. These are different for different topographic areas. If the topography is planar in nature, one rain gauge is needed to cover about 520 square kilometers. If the topography is elevated in nature, that is, if the area is elevated, that is, if it is 1000 meters above mean sea level, then one rain gauge is needed to cover an area of 260 to 390 square kilometer. Similarly, if the area is hilly or very heavy rainfall areas, then one rain gauge is needed to cover about 130 square kilometer. And preferably, there should be 10% of rain gauge stations equipped with self-recording gauges to know the intensities of rainfall. Now, for this, we have also World Meteorological Organization, which has recommended the density of rain gauge based on the nature of the topography. If the topography of the area falls under temperate or Mediterranean or tropical area, then one rain gauge is needed to cover an area of 600 to 900 square kilometer, while the acceptable range is 900 to 3000 square kilometers. If the area falls under temperate or Mediterranean or tropical, then the ideal condition is one rain gauge station is needed to cover 100 to 250 square kilometer, while the acceptable range is 250 to 1000 square kilometers. If the area falls under arid or polar zones, then one rain gauge is needed to cover an area of about 1500 to 10,000 square kilometers. Now we will talk about average annual rainfall. Now, what do we mean by average annual rainfall? Average annual rainfall means it is nothing but it is a mean of yearly rainfall for a period of 35 consecutive years. This average annual rainfall depends on a number of factors. Some of them are distance from the ocean, direction of wind, mean annual temperature, altitude, and topography. Now, how we are going to classify a particular year as wet, dry, or normal is based on the intensity of rainfall. Similarly, we can classify into different categories like arid, semi-arid, or humid on the basis of the intensity of rainfall. So, if the rainfall is more than average annual rainfall, then that particular year is termed as wet year or good year. If the rainfall is less than average annual rainfall, then that particular year is termed as dry year or bad year or difficult year. Similarly, if the rainfall is more or less equal to the average annual rainfall, then that particular year can be termed as normal year or average year. Similarly, we can classify the climates into three categories. If the rainfall is less than 40 centimeter per year, then that particular climate can be classified as arid climate. If the rainfall is between 40 to 75%, then such climate can be categorized as semi-arid climate. And if the rainfall is more than 75 centimeter per year, then the climate can be termed as humid climate. Now, there is a term index of wetness. What do we mean by index of wetness? It is nothing but it is the ratio of rainfall in a particular year to average annual rainfall. For example, if an index of wetness of 60 in a year indicates a rainfall deficiency of 40%. Again, I am repeating, An index of wetness of 60 years in a year indicates a rainfall deficiency of 40%. Now, based on the intensity of rainfall, the rainfall can be categorized into three categories. If the intensity of rainfall is traced to 2.5 mm per hour, then such type of rains are classified as light rain. If the intensity of rainfall is between 2.5 to 7.5 mm per hour, then such type of rains are termed as moderate rain. While if the intensity is more than 7.5 mm per hour, then this type of rainfall is termed as heavy rain type. Now we will discuss about the journey of rainwater or the precipitation to groundwater, that is subsurface condition. When the cloud precipitates, we get rainwater. This rainwater is very pure in nature, and this can be compared with the distilled water. However, during its journey from atmosphere to the surface of earth to the subsurface, it picks some salt from the atmospheric aerosols, commonly of sodium chloride type, as other cations and anions are not found in atmosphere. The electrical conductivity of such water, that is such rainwater, is commonly low. But in highly polluted air, because of industrial pollution, the rainwater becomes very rich in sulfate and nitrate, and then it will have low pH. Since chloride is most conservative element present in water, when composition of chloride in sea and rainwater against TDS is compared, then it becomes very clear that rainwater can be treated as a dilute solution of seawater. The rainwater continuously changes during its journey as it flows through different rock formations. During its journey to groundwater reservoir or the groundwater aquifer, there is some addition or subtraction of some chemical constituents. This addition or subtraction of chemical constituents takes place by number of processes. That is, we can say that there are various processes which are responsible for this addition or subtraction of chemical constituents during the journey of rainwater to the groundwater reservoir. So the first process is weathering and dissolution of minerals and rocks. The second process is evaporation. The third one is selective uptake of ions by vegetation. The fourth is decay of organic material. The fourth one is ion exchange. The fifth one is mixing of different water qualities, and the seventh one is anthropogenic contribution. So we are going to discuss these processes one by one, which are responsible for the addition or subtraction of chemical constituents during its journey from surface to subsurface. The first process is weathering and dissolution. We all know that 99% by weight of earth crust, it is composed of mainly 8 elements, and these 8 elements combine together to form various minerals. These important 8 minerals which constitute the earth crust are oxygen, silica, aluminium, iron, calcium, sodium, potassium and magnesium in decreasing order. Now this table indicates the average composition of some igneous and some sedimentary rocks, which mainly composes or constitutes the earth crust. Now the chemical weathering of these rocks, that is the igneous rocks, the sedimentary rocks or the metamorphic rocks, by the rainwater containing dissolved acid on rock minerals, these release soluble ions to groundwater. This chemical weathering of rocks by the rainwater, which contains dissolved acid, depends upon the residence time of water also. That is, if the residence time is higher, there will be more chemical weathering. If the residence time of the water is less, then chemical weathering of the rocks will be naturally less. So the water which we get in the weathered ultra basic formation will be rich in magnesium. Similarly, the water which we get from the limestone area will be rich in calcium. The water which we get from dolomite area will be rich in calcium and magnesium, while the water which we get from granitic area will be rich in sodium and potassium, and the water which we will get from quartzitic area will be very pure, and it can be compared with the rainwater as far as the purity is concerned. The second process is evaporation. Because of the process of evaporation, the groundwater becomes rich in chloride. This process of evaporation is very fast in shallow water condition. When groundwater comes to soil zone by capillary action, it leads to evaporation process. Because of this evaporation, salt deposits in the soil profile, which is finally dissolved by the rainwater, and it finally added to the groundwater. The third important process is selective uptake of ions by the vegetation or by plants or by biomass. There are some elements like nitrogen and phosphorus which are especially selected by biomass or by plants during the uptake of soil moisture and are used in the formation of organic material. So a large amount of potassium is taken by vegetation from the soil, but this is not stored in the organic material, but it is released from the plants through the process of transpiration. So very little amount of potassium is present in groundwater, though most common rock type, for example granite, contains very high amount of potassium in the form of orthoclase. The fourth important process is decay of organic materials. The organic materials, due to the process of oxidation reaction, decays or decomposes to carbon dioxide and water. This can be represented by an equation, that is, organic material is equal to carbon dioxide plus water. The infiltrating rainwater takes this carbon dioxide in the form of carbonic acid and is released to groundwater. Thus, water plus carbon dioxide is equal to carbonic acid. Any calcium carbonate in soil profile dissolves with the acid, and thus groundwater gets enriched in calcium bicarbonate. This can be represented by a simple equation: calcium carbonate plus carbonic acid is equal to calcium bicarbonate. This calcium bicarbonate is very soluble in water. Another fifth important process is ion exchange. We all know that sodium and calcium have similar ionic radii. So the exchange of these ions between groundwater and clay minerals is very common. This can be exemplified by the process of freshening of aquifer system. Here the presence of saline water, which is rich in sodium, leads to high amount of sodium in clay present in the aquifer matrix. But when fresh water, which is rich in calcium, enters and replaces saline water, which is rich in sodium, the sodium present in the clay lattice is replaced. So the groundwater becomes rich in sodium and bicarbonate, and such type of groundwater is known as sodium bicarbonate type water, indicating freshening of the aquifer system. The reverse situation of this is during intrusion of saline water into fresh water aquifer, where calcium chloride type water is found. Cation exchange is most common in groundwater as compared to anionic exchange. The another important process is mixing of water of different qualities. Such type of mixing occurs in seepage zones or in springs or in alluvial areas having both fresh and brackish water which exist side by side. This mixing can lead to undersaturation with respect to calcite, even if waters were individually at saturation before mixing. This leads to renewed dissolution of calcite. Another important process, as we all know, is anthropogenic contribution, that is, the contribution made by the human being. We know that sewage water adds chloride and nitrate to the groundwater. Similarly, heavy use of fertilizers adds nitrate and phosphate into the groundwater. So now, here in Gibbs plot, which is nothing but the mechanism of governing the groundwater chemistry. This Gibbs plot was given by Gibbs in 1970. Here the electrical conductivity or the total dissolved solid plot against sodium by Na plus Ca and Cl plus bicarbonate of water samples. has been shown. 3 processes related to groundwater quality can easily be identified. The first is precipitation water in sodium chloride type with low electrical conductivity, which has been shown on the right hand side and the lower side of the diagram. The central part, as shown in the figure, is rock dominated with calcium bicarbonate type groundwater. And the third one is evaporation causes precipitation of carbonates and groundwater continues to be rich in soluble salts and thus becomes sodium chloride type with high electrical conductivity. Now we will talk about water quality standards, which depends on the presence of various chemical constituents. The water quality which may be useful for irrigation may not be useful for drinking purpose or may not be useful for industrial purpose or for industrial boilers. For example, groundwater having iron more than 0.3 ppm may be useful for irrigation, or the groundwater with low TDS and low sodium with high calcium may be useful for irrigation purpose, but such type of groundwater may not be useful for drinking purpose, or such type of groundwater enriched in high calcium may not be useful for industries or for industrial boilers, because such groundwater with high calcium may produce scaling effect. Now, drinking or potable water standards. Number of standards has been adopted and developed during the course of time. The drinking quality means the water which is useful for drinking as well as for cooking. The potable water means that type of water should be clear or free from any bad smell or bad taste, that should be free from chemicals having adverse effects, that should be free from elements causing corrosion or causing cloth staining, or that type of water should be free from disease causing organisms. As we have discussed that number of standards have been developed. One standard has been developed by the health and sanitary authorities based on the relationship between waterborne diseases and drinking water. World Health Organization has published guidelines for drinking water quality. The first edition of this was published in 1983-1984. The second edition of the guideline published by the World Health Organization came into 1993-97 in the form of second edition, followed by another edition which came in 2004. We have also Indian standards which is known as BIS standards. The first edition of which came in 1993, followed by second edition in 2009, which is also known as IS 10500 quality standard. Now this table is showing the various substances with their acceptable and their permissible limits with their negative impact or effect on the organisms or on the vegetation or plants. Now we will talk about irrigation water quality standards. Here we will discuss the quality standards of groundwater for various purposes, especially for irrigation, on the basis of chemical characteristics capable of creating hazard to crops. These chemical characteristics are, the first one is salinity, which is nothing but the total concentration of soluble salts. The second characteristic is Sodacity, which is nothing but concentration of sodium relative to calcium and magnesium. The third characteristic is relative proportion of carbonate plus bicarbonate to calcium and magnesium. The fourth important chemical characteristics is concentration of boron and other elements that may be toxic to the plant growth and their yield. So we are going to talk all of this one by one. First chemical characteristic is salinity. The salinity is nothing but it is the presence of salt, that is the amount of salt which is present in the groundwater. The effect of salts on the various type of crops or their growth is osmotic in nature. The osmotic potential of soil water solution at root zone is related directly to the electrical conductivity of irrigation water. As water is removed from soil by the process of transpiration or by the process of evaporation from soil surface, the salt concentration of soil solution at root zone rises, maybe up to 2 to 5 times than that of irrigation water, resulting in fall of osmotic pressure. This fall of osmotic pressure leads to alteration of hormone balance, causing damage to plant tissues and growth of specific ions potentially toxic to plants and their yields. These effects are also visible in plants by stunted growth, by low yield, by the discoloration of the plants, or even leaf burn at the margin or at the top. The another chemical characteristic is sodacity. The excess of sodium in water is unsuitable for irrigation on soil containing exchangeable calcium and magnesium ions, as soil takes up sodium of water in exchange of calcium and magnesium ions of soil, and thus causes deflocculation and impairment of the tilth and permeability of soils. When concentration of calcium and magnesium in soil solution is less than 1 milliequivalent per liter, then the plants may show calcium deficiency symptoms. Thus, effects of sodium on plants are indirect, as it affects plants' nutrition balance at soil water zone and brings about adverse changes in soil characteristics. For knowing the sodium hazards, United States Salinity Laboratory has recommended sodium absorption ratio. The irrigation water containing high concentration of bicarbonate has a tendency for calcium and magnesium to precipitate in the form of calcium carbonate and magnesium carbonate. For knowing the effect, an empirical parameter was devised by Eaton in 1950 on the assumption that all calcium and magnesium will precipitate. The parameter is termed as residual sodium carbonate, which can be represented by the following formula. Residual sodium carbonate is equal to carbonate plus bicarbonate minus calcium plus magnesium, where the concentration of these are in milliequivalent per liter. When excess carbonate or residual carbonate concentration becomes too high, the carbonates be combined with calcium and magnesium to form a solid material, which can be in the form of scale and which settles out of the water. The end result is an increase in sodium absorption ratio. The USDS has established guidelines for modifying water quality classifications based on residual sodium carbonate expressed in units of APM. The residual sodium carbonate level, if it is less than 1.25 BPM, then they are considered as safe groundwater. The water with residual sodium carbonate range between 1.25 to 2.5 BPM, then they are said to be within marginal range. These waters should be used with good irrigation management techniques and soil salinity monitored by lab analysis. The risk is lowest with waters for which residual sodium carbonate is at low end of the range and which are being applied to permeable, well-drained, coarse textured soils in high rainfall areas. The residual sodium carbonate values of 2.50 APM or more are considered too high, making the water unsuitable for irrigation purposes. The modification of residual sodium carbonate by soil applied gypsum may permit use of waters with residual sodium carbonate values above safe. Now we will talk about the quality of irrigation water. The quality of irrigation water has been classified into various classes based on some parameters. These parameters are sodium percent, salinity hazard, electrical conductivity, sodium hazard class, sodium absorption ratio, and residual sodium carbonate. So based on these parameters, water classes have been developed, and there are 5 classes ranging from excellent to good to medium to bad to very bad. So these are the 5 water classes based on various parameters. Now, to assess the sodic and salinity potential of irrigation waters, US Salinity Laboratory in 1954 adopted an irrigation water classification based upon sodium absorption ratio and electrical conductivity. This is known as conductivity and salinity classification. This classification is extensively used worldwide and consists of 16 groups of irrigation water. Now, based on this, the groundwater have been classified into 4 categories. The first one is low sodium water with low to very high salinity. This type of groundwater is suitable for irrigation on almost all types of soil, with little danger of development of harmful levels of exchangeable sodium. However, sodium sensitive crops may accumulate injurious concentration of sodium. There is no likelihood that salinity will develop with low saline waters, but as salinity potential of irrigation water increases from low to very high level, it requires adequate drainage, permeable soil and selection of salt tolerant crops. The second category is medium sodium water with low to very high salinity. These water are useful only on well-drained soils with low cation exchange capacity and can be used satisfactorily on coarse texture soil with good permeability. These waters will present appreciable sodium hazard in fine textured soils with high cation exchange capacity, especially under low leaching condition. The third category of groundwater, irrigation groundwater, is high sodium water with low to very high salinity. This type of water is useful only in special cases under good soil water management, that is with soil with good drainage, high leaching, addition of organic matters, etc. More suited for gypsiferous soils, otherwise they may develop harmful level of ESP in most soils. The chemical amendments are feasible only at low saline conditions. Now the fourth category is very high sodium water with low to very high salinity. This type of groundwater is generally unsuited for irrigation purposes except at low level of salinity, where their use may be feasible on gypsiferous or calcareous soils. Now we'll talk about the hazard which may be created by boron. We know that boron is present in all natural water as boric acid. The boron is an essential plant nutrition if at very low level. However, it becomes highly toxic at concentration slightly above the optimum value. The parts of boron from irrigation water get fixed with soil material, and due to this, the water containing marginal level of boron may not be immediately toxic. But after a long duration of irrigation with such type of water, new equilibrium will be established where soluble boron level may exceed than those of irrigation water. Hence, long use of water containing more than 3 ppm boron is not recommended. The quality criteria adopted for boron has been developed by Richard 1954 and Wilcox 1960, which is being adopted in various parts of the world. Based on the tolerance limit to boron, various plants have been categorized as sensitive, semi-tolerant or tolerant variety of crops to boron. Another type of hazard may be developed due to the magnesium. This is normally calculated as magnesium divided by calcium plus magnesium into 100, where all the concentrations are in APM. And the magnesium hazard more than 50 is very harmful to plants. So with this, I'd like to conclude my talk. Thank you very much. Have a nice time.